Hello students, this is Mr. Allen. Today we're going to wrap up chapter 7 and we're going to look at something called improper integrals. Improper integrals. Our goal or objective today is to evaluate an improper integral that has an infinite limit of integration and evaluate an improper integral that has an infinite discontinuity. So we got two types of improper integrals. So the definition of the definite integral is the integral from a to b of f of x dx requires that a and b be finite. In other words, it requires that a be some value, some number. So a is some number and b is some number. So if it's not some number, we've got an issue. A procedure for evaluating integrals that don't satisfy these requirements, usually because either one or both of the limits of integration is infinite, or if we have a point of discontinuity, these are called improper integrals, but we're going to address those in this section. So a function f is said to have an infinite discontinuity at c if the limit of the function as x goes to c is infinite or negative infinity. So this is, if you recall, when we talked about vertical asymptotes, this was our definition of a vertical asymptote. In other words, we're going to figure out how to do integrals potentially that have discontinuities as such. So here are some definitions. So here you can see that if we're going to integrate from a to infinity of f of x, we're going to change that to the limit of an integral. Similarly, if we're going to go from negative infinity to b, we're going to change that to a limit as a goes to negative infinity. Or we can even do both, going from negative infinity into infinity. In the first two cases, the improper integral converges if the limit exists, otherwise it diverges. In the third case, the improper integral on the left diverges if either of the improper integrals on the right diverges. So let's look at our first example. This is an improper integral because we're taking this integral to infinity. Remember, infinity is not a number. So what we're going to do is we're going to go back and we're going to use our first definition, and we're going to change this integral to the following. The limit as b goes to infinity of the integral from 1 to b of dx over x. And now we're just going to take this limit b going to infinity to deal with this. So what is the antiderivative of 1 over x? That, of course, is the ln of x, and we're going to evaluate that from 1 to b. And when we get that, we're going to get the ln of b minus the ln of 1. Of course, the ln of 1 is 0. This is based on the fundamental theorem of calculus. And now we need to evaluate this limit as b goes to infinity. Well, the ln of infinity is itself infinity, and infinity minus 0 is infinity. So the answer here is infinity. In other words, this diverges. I think I just spelled diverses. Diverges. There we go. It diverges. In other words, we cannot associate a value to this particular integral, which is pretty interesting, actually, when you think about it. So if we think about the curve, so this would be, and by the way, this curve would also be this part over here, but since we were only integrating from 1 to infinity, this area here turns out to be infinite, which is, I think, kind of surprising. All right, so now let's talk about the definition of improper integrals with infinite discontinuities. So now what we're going to do is, instead of necessarily integrating to infinity or integrating from negative infinity, what if there's a discontinuity, an infinite discontinuity somewhere in the middle? So this is going to be the formula, which is very similar to what we saw in the past. Let's look at an example. So here, this looks like that this should be a regular integral, definite integral. There's a problem, though. Where is the problem? Well, I hope that it's pretty clear that at x equals 0, we're going to have an issue. Okay, and I hope you can look at that and say, well, you'd have dx over 0, basically, right? So you're actually asking, I mean, if you think about what this curve looks like, and I'm just going to go ahead and jump ahead. Here's what this curve looks like. At 0, this is has a vertical asymptote because the limit on the right is infinity. So this is an infinite discontinuity. So to evaluate this integral, we're going to go back and we are going to use one of these. And in this case, we're actually going to use case B. So we're going to evaluate this integral as such. So we're going to say the limit as b goes to 0 plus. So we're going to come in from the right-hand side. And the antiderivative of x to the negative 1/3 is x to the 2/3 divided by 2/3. We're going to evaluate that from 1 to b. That gives us the limit as b goes to 0 plus of 3/2, and then quantity 1 minus b to the 2/3. And if I take b go to 0, that's going to give us a final answer of 3/2. So this is very interesting. So I'm telling you that this area here, this area is the finite area 3/2. However, if we go back to the previous example, we found that this area here was infinite. So this is, I guess, the thing I would like to point out to you to be aware of. Don't be too quick to jump to conclusions with these improper integrals. They are not necessarily intuitive. In fact, I would argue that they are not intuitive, and this is what leads to a lot of consternation for students in this class. It seems like this area to me looks bigger. It seems like it should be finite, or I'm sorry, infinite. But the other one, which looked smaller, actually was infinite, and this one was finite. And by the way, there's a big difference between 3/2 and infinity, which is very interesting, I think. Theorem 8.5 is a special case or special type of an improper integral. And it's when you have the integral from 1 to infinity of 1 over x to the p, where p is some positive integer. Turns out that if p is, and I guess it doesn't even have to be positive, if p is greater than 1, and it doesn't even technically have to be an integer, so let me fix this. P can be a real number. If p is greater than 1, this thing is going to divert or converge, and it will converge to this. So let me give you an example. If I said, what's the integral from 1 to infinity of 1, dx over, let's say, x to the second. So here we would say that p is greater than 1. I am telling you that this is going to be equivalent to 1 over, and notice that p is 2. It's going to be p minus 1. So the answer is 1. That integral is 1. However, if I change this integral to something else, let's say it's from 1 to infinity of dx to the above the x to the, let's say, 0.9, this diverges, so it's d and e. 0.9 here. Okay. So last application here we're going to look at something called Gabriel's horn. I would highly encourage you, if you find this example interesting, I find this one extremely interesting, because this leads to a paradox, and there's been a number of YouTube videos made about this. And it says the solid form by revolving about the x-axis, the unbounded region lying between the graph f of x equals 1 over x. So this is the graph of 1 over x. So f equals 1 over x. And the x-axis, when x is greater than 1, is called Gabriel's horn. Show that this solid has a finite volume and an infinite surface area. So let's go ahead and do that. Let's find the volume first. Okay. So to find the volume, we would just use the disk method. Remember, the disk method is just simply pi r squared, and then you integrate from a to b. So in this case, we're going to integrate from 1 to infinity. That's what makes it an improper integral. So we're going to go ahead and use the theorem that we just used on this previous slide, this theorem 8.5. And since this case, it's, remember, when we square this, this is essentially 1 over x squared. So p is going to be 2. So we're basically doing the problem I just did. So I'm telling you that the volume of Gabriel's horn is pi. Very finite, 3.14159, etc., right? That's the volume. Now let's look at the surface area, which we just talked about at the very end of chapter 6. So to find the surface of revolution, we're going to use the following formula. This should look familiar to you. And our f of x here is 1 over x. And then we're going to do 1, and we got to do the derivative of this squared. And you're going to get, remember, if we do the derivative, that's going to be negative 1 over x squared. But then we're going to square that, so that's going to make that positive. All right, so because the square root of 1 plus 1 over x to the 4th has to be greater than 1 on the interval from 1 to infinity, then the improper integral 1 to infinity 1 over dx diverges. It's going to diverge. In other words, it goes to infinity. This is greater than 1. So this right here is greater than 1. We already know what's going to happen. We already know that this diverges. We've already looked at that. So we've got infinity times something that's greater than 1, which is going to be, in other words, what I'm saying is some number greater than 1, let's just say 2. What's 2 times infinity? Well, it's infinity, right? So we can conclude that this surface area diverges. Now, you might think that that's kind of an interesting thing, but here's what I'd like you to consider. Let's go back and look at Gabriel's horn. So we just concluded that the volume of Gabriel's horn, the volume, was pi. We've just concluded that the surface area is infinity. So here's what I'd like you to think about. Listen carefully to what I'm going to say. And remember, pi is approximately 3.14. I am telling you, if you were going to fill Gabriel's horn with paint, fill it up with paint, you would need just over 3 gallons to fill it up, the volume with paint. However, if I asked you to paint the surface area of Gabriel's horn, guess how much paint you would need? Think about that. The volume of liquid it can hold is 3.14159, etc. But the surface area, in other words, the paint that fills Gabriel's horn isn't even close to being enough to paint the horn. I think that is a great place to stop.